Okay, we will continue with the shunt and series and separately and finally compound excited DC motor and generator operations. So for the separately excited DC machine, if we remember the equivalent circuit, we have on the field side, the stator part, we have RF and LF. RF also can be drawn as an adjustable resistance to control the field current. Because of the separately excitation, there will be no electrical connection between the field and the armature side. And we need an external additional source for the field side in addition to the terminal part. So IF will flow through the field winding, induced internal generated voltage, armature resistance, and VT, which represents the terminal voltage. Until to here, we don't have any difference in motor or generator operation. So if we have a motor operation, IL and IA must show inside the circuit we will supply from here, and we will obtain mechanical energy for the motor operation. But if we have a generator operation, IA and IL, which represents the armature current and the line current, must show the out of the circuit for the generator operation, because we will take the electrical energy from the terminal part. When we examine the equations, for the right part, armature side, Kirchhoff's voltage law can be written as Vt, and the other two components will be Ra and RaIa. For the motor operation, the sign between these these parameters must be plus, while the generator operation, the sign must be minus, because EA will be the main supply during the generator operation. To show the current relation of this parts, rotor and the generator, we can write IA will be equal to IL. And for the field side, VF will be RF and IF. In addition to that, we can write the inductance voltage drop, but during the steady state, that part must be zero. Okay, so in the motor and the generator operation, we have only different cases in the first expression. For the right side, because of the current reversal issue, we have positive and negative. What about the shunt excited operation? For shunt excited operation, let's start with the equivalent circuit again. So for the machine, now our parts, armature and field components must be connected in parallel. In the shunt excited case. And for the terminal, again, we have a DC voltage. We can take out or we can apply according to operation type. And let's examine the operation. By the way, for the motor or generator, doesn't matter. IF direction will not change. For the motor, IA and IL will come from the terminal part during the motor operation, but for the generator operation, IA and IL must be out of the circuit. And because of this, we can use the first expression, VT is equal to EA and RA expressions in the shunt excited operation also. So VT, EA, RA, IA will be the parameters for the big loop in the circuit on the left side. And again, for the motor operation, the sign between these parameters must be plus because the main supply will be VT. The input will come from the VT. But for the generator operation, the sign must be minus because EA in that case will be the main supply. Okay, for the second expression of the shunt excited DC machine, we can continue with the current relations. For the currents, if you write the Kirchhoff's current law for this node, you can write IL, IA, and IF. This will be the motor operation. But for the generator, IA will be the main supply, and the expression must change in that case like this. For the last one, the field current relation, field current expression, VT, the terminal voltage, will be the field side voltage, field winding supply also because of the parallel connection of the circuit. So because of this, VT, the terminal voltage in that case, will be RF times IF. Again, the inductance voltage drop can be integrated, but during the steady state, if we want to analyze, we don't need to keep that part because the inductance voltage variation will be 0 because of the DC system. Okay, let's examine the terminal characteristics of the DC machine. In that part, we need to analyze as a motor and the generator because the terminal characteristics, the output characteristics for the motor operation will be torque speed characteristics. For the generator, output voltage and the current characteristics will be. So for the terminal characteristics of the DC motor, terminal characteristics for the motor operation, it will include the torque increments. So if we increase the output load, what will happen? Our internal developed induced torque must be increased. We need higher torque to be able to supply this higher load. So our induced torque must increase. And we know the relation between the torque and the internal parameters, which is K, phi, and armature current. For the constant flux, if we examine the system, for the constant flux, armature current must also increase to be able to supply this higher torque. Then, what will happen? Let's check the first expression here for the motor operation. VT minus EA over RA can be written for the armature current. So because of this, we can continue with the EA because the relation between IA, the armature current, and the EA will be reversed. EA must decrease because of the negative sign. And according to our one of the important expressions, EA is equal to machine constant, flux, and the angular velocity. So we can say the Wm, the machine speed, must decrease also. Okay, but how much it will decrease? to find an expression about it, we can start with the voltage expression, which is VT, EA, and RA, IA expression. And we can write our additional expressions for EA, K phi WM, and for armature current. For armature current, we can write the induced torque divided by K and phi. So let's rearrange the expression to find an expression for WM, motor speed. What we will obtain, Vt over K times phi minus Ra over K phi square and induced torque. So from here, we can determine how much variation we will obtain when we increase the induced torque step by step. And there will be a negative slope between the induced torque and the WM. What about the generator operation? For the generator operation terminal characteristics, we will examine the output voltage, that means the terminal voltage, and output current. So for DC generator, again, the relations must start with the output load increment. So if we increase the load related parameter should be the output load current, line current, which is flowing through the terminal point, must increase. So we will increase the load current step by step. Then what will happen? First of all, let's think about the separately excited version. IL is exactly equal to IA. So that means IA must increase to be able to supply this higher load torque. Then, if we increase the IA, our terminal voltage must decrease from the first expression. Vt will decrease during that operation in the system. Then what will happen? IF must decrease when we examine the current and the voltage relation. Then after that, because of the decrement in IF, Vt will decrease more for the shunt excited version. So initially, when we increase the IL until to blue line, IA must increase, and as a result of this, generator voltage expression says us the separately excited DC generator output voltage will drop. How much? It will start from the no load voltage value and it will decrease according to RA times IA. How much you increase IA? With the multiplication of RA, the system, the output voltage will remain if your connection is separately excited. But if you have a shunt excited connection, the process must continue. Why? Because the terminal voltage drop will affect the IF. In the separately excited system, IF supplied by a constant external source, so it's always constant. But for the shunt excited, we are using the same terminal voltage, so because of this, when the terminal voltage decreased, IF also will decrease. Then, because of this decrement, according to our internal generated voltage expression, which is EA, and it is relation with IF, the Vt, the terminal voltage, must decrease more because of this expression. Vt has decreased, and in addition to that, EA decreased. So the decrement in Vt will be more in that case. So because of this, we can show the shunt excited output voltage decrement when we increase the load current step by step until to rated value. And this next decrement will happen because of the flux weakening effect inside the machine. And for the shunt excited system, we have more decrement in terms of the output terminal voltage. Okay, what about the third group? Series excited DC machine. For series excited, what we will do, we will connect our armature and field windings in series. So let's start with the armature part with EA and RA. Then we can continue with the series connected field side. And the terminal voltage will be here. And similarly, if we have a motor operation, IL must show inside of the circuit, and the current flowing through the series components, current flowing through the armature current will be in the same direction with line current. And for the generator operation, only the current flowing through the circuit will be reversed. And if we want to write the voltage equation, it can be written as Vt must be equal to EA and all the voltage drops current times current voltage drop values. And the sign between them for the motor operation will be plus. For the generator, it must be minus because the main supply will be EA during the generator operation. And the last excitation type can be defined as compound excited, which includes series and parallel connection at the same time. For the compound excited DC machine, we have some subgroups, but briefly, we can say we have again internal generated voltage EA and RA, which are the components of the armature circuit. Then we have a series, then the parallel connection, let's say. So this is one of the compound excited DC machine equivalent circuit. VT, RF, LF, the current flowing through that part, RS, LS, and the current flowing through that part will not change during in motor or generator operation. For the motor operation, the current will show inside of the circuit, so it will be same with this direction, but IF and the EA polarities will not change. For the generator operation, IA and IL will be reversed. In addition to that, for the compound excitation, we have here a long shunt connection. Why? Because after we connect everything, after a long connection, after the series connection, we have the parallel connection. So it's called as long shunt compound excitation. If we slide that part, this parallel connection, after the armature winding, if we connect first of all parallel, then the series, the connection will be called as short shunt excitation. And according to polarities of Ls and Lf, if they support each other, we have a cumulative excitation. If their directions are reversed, if their polarities are different with respect to each other, if their effect are decreasing, mitigating their magnetic fields, in that case we have a differentially compound excitation. But for the compound excitation, briefly we can say we have series and parallel connected field sites in the same machine for the compound excitation. Thank you for watching.